Hello everyone, this is Professor He again. Welcome back. The topic of this task is about the properties of a system. Any characteristic of a system is called a property. Some familiar properties are pressure P, temperature T, volume V, and mass M. The list can be extended to include less familiar ones such as viscosity, thermal conductivity, modulus of elasticity, thermal expansion coefficient, electric resistivity, and even velocity and elevation. Properties are considered to be either intensive or extensive. Intensive properties are those that are independent of the mass of a system, such as temperature, pressure, and density. Extensive properties are those whose values depend on the size or extent of the system. Extensive properties per unit mass are called specified properties. Some examples of specific properties are specific volume and specific total energy. Total mass, total volume, and total momentum are some examples of extensive properties, and either way to determine whether a property is intensive or extensive is to divide the system into two equal parts with an imaginary partition as shown in the figure. Each part will have the same value of intensive properties as the original system, but half the value of the intensive properties. Generally, uppercase letters are used to denote extensive properties, and lowercase letters are used for intensive properties. As noted earlier, the state of a system is described by its properties. But we know from experience that we do not need to specify all the properties in order to fix a state. Once a sufficient number of properties are specified, the rest of the properties assume certain values automatically. That is, specifying a certain number of properties is sufficient to fix a state. The number of properties required to fix the state of a system is given by the state postulate. The state of a simple compressible system is completely specified by two independent intensive properties. A system is called a simple compressible system in the absence of electrical, magnetic, gravitational motion, and surface tension effects. These effects are due to external force fields and are negligible for most engineering problems. Otherwise, an additional property needs to be specified for each effect. That is significant. If the gravitational effects are to be considered, for example, the elevation Z needs to be specified in addition to the two properties necessary to fix the state. The state postulate requires that the two properties specified be independent to fix the state. Two properties are independent if one property can be varied while the other one is held constant. Temperature and specific volume, for example, are always independent properties, and together they can fix the state of a simple compressible system. Temperature and pressure, however, are independent properties for single-phase systems, but are dependent properties for multi-phase systems. At sea level, water boils at 100 degrees centigrade, but on a mountain top where the pressure is lower, water boils at a lower temperature, that is, T equals Fp, during a phase change process. Thus, temperature and pressure are not sufficient to fix the state of a two-phase system. For a fixed state, all the state properties are then determined. Then, an arbitrary state property is. A state property is a state or point function. The state property is only concerned with the state and is not related to the path of reaching the state. For any state property, its total derivative is. The order of differentiation is immaterial for properties since they are continuous point functions and have exact differentials. Therefore, we have. This is an important relation for partial derivatives, and it is used to calculus to test whether a differential dz is exact or inexact. In thermodynamics, this relation forms the basis for the development of the Maxwell relations discussed later. The change of the state property is independent of the path and only related to the initial and the final states. The topic of this subtask is about the commonly used state properties and their relations. 8 commonly used state properties are temperature T, pressure P, specific volume V, specific internal energy U, specific enthalpy H, specific entropy S, specific Helmholtz function F, specific Gibbs function G. The interrelations are shown in figure 1-6. You can start with internal energy U going anti-clockwise as shown here, then H, G, F, and end with U. You can also start with internal energy U going clockwise, then F, G, H, and end with U. Okay, that's all for this task. Thank you very much, and see you next time.